One of the things that's really important when you use large databases and SQL databases is the ability to create index. Now, for most of us using GIS, we haven't really had to worry about indexes lately because computers are really fast. In the old days, when I first started using GIS back in the late 80s and 90s, indexes were very important because computers were slow. Um, Now the issue is computers have gotten faster, but our data has gotten bigger. So we almost have to kind of go back to the past and learn some lessons from that time and begin to start using things like indexes. And one type of an index we can create is called a binary search tree. These are ways to make our data searches go really fast, and it's a really cool part of SQL databases. So let's assume we have a whole bunch of numbers, this 8, 3, 6, 10, 1, 14, 7, 4, and 13. Now, if I want to find the number 3, I'm in pretty good shape. I go to 8 and I go to 3. It takes me 2 steps. This is called a serial search. Now the problem is if I want to find 13, well, that's another story. I've got to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So that takes a bit longer. So what we're saying when we think about a serial search is that on average, finding a data value is really n divided by 2. And we call that order, n divided by 2. That's the computer science term, which we call order notation. In other words, if I have 9 records, it's going to take me on average about 4.5 searches to find the actual record. That's because sometimes I grab it on the first try, other times I grab it on the last try, but on average, order n divided by 2. Now, one thing that computers can do is actually store data in what was called a data structure. If you were a computer scientist, you would learn about these in some of your classes. And one of those types of data structures is this binary search tree. So imagine we take the same data we were looking at. The first record is 8. That goes into a memory location, and then there are things called pointers, which are basically directives within a computer code that will point to memory locations because memory is super fast. So we have fast access. Well, the number 3 comes in. Now 3 is less than 8, so we're going to dive to the left because it's less than 8. Now 6 is also less than 8, so it comes in here, it dives to the left, but now it dives to the right because 6 is greater than 3. Now 10 comes in, and that's greater than 8. That's pretty easy. 1 comes in, it's less than 8, it's also less than 3. 14 comes in, again, greater than 8, greater than 10. 7, of course, is less than 3, less than 8, greater than 3, and greater than 6. 4 is less than 8, but it's greater than 3, but it's less than 6. So these are all pointers that you can see here that are pointing to memory locations where the data is actually stored. So again, imagine we're looking for the number 4. In a serial search, it would be 1, 2, 3, 4, 5, 6, 7, 8 steps. If I'm looking for this number 4 now, it would be 1, 2, 3, 4. If I'm looking for the number 7, 1, 2, 3, 4, where I have about 7 searches. The number 10, instead of 1, 2, 3, 4, it's 1. So this actually has an order notation of the order of the natural log of n. So in this case I have 9 records, and let's take a look at that. So again here, 9 divided by 2 is 4.5 steps on average in a serial search. Now let's look at 9, and the natural log is 2.19. So on average we're about 2.19. So in this case it's twice as fast. Now let's look back at some larger data. Let's assume we have 10 million records. Now a serial search divided by 2 means it's going to take 50,000 iterations to find data value on average, right? Because sometimes it might be the very first one, but other times it might be the very last one. Let's multiply that by 2. So 50,000. Now, actually, let's do that again. 10 million, and we divide by 2. That's better. That's going to take 5 million times on average. Now 10 million, and let's look at the natural log. 16. So you're looking at 5 million compared to 16. Is this even possible? Yeah, it really is. And let's take a look at what we mean by that. Now, unfortunately, the data set that we're working with is not terribly large. So I'm going to work with another data set. This is part of my big data class that I often teach. If I look at the properties of this table, which is the yellow trip taxi data from 2012, we can see under properties that it has about 11 million records. So that's a pretty large, that's just estimated. There's actually more than that. That's a pretty large data set. Now I can type something like this, select star from yellow underscore trip data underscore 2012 underscore 10, and then let's say limit 100. That's fine. Let's just look at some of the records that we have in the database, and there it is. You've got, so these are all the taxi pickup and drop-offs. You got the drop-off and the pickup date and times, the number of passengers, the distance, lots and lots of stuff. But one thing that we're going to be interested in is the zone. So they pick up from Greenwich Village or Sunnyside or somewhere like that. Now if we look under yellow trip data, I actually created an index called zone underscore IDX. And I created the zone index this way, just create index zone ID underscore IDX. I like to do that so I know it's an index on yellow trip data, and this is the column name. Now another way you can create indexes as well is you can come in here and say create an index, and then you can set up a definition, whether it's a B tree or any other kind of index. So I'm going to cancel that right now. But let's just rest assured there is an index called zone or zone underscore IDX, and it works on the zone field. So let's first select the count of all the pickups that occurred in Greenwich Village. So we have a zone in there, or excuse me, not Greenwich Village, of Sunnyside. So I'm going to run this, and I want to get the count. I'll run that, and that completed in 117 milliseconds. Now I've also got, let's say, select star from yellow trip data underscore 2012 underscore 10 limit 100. Let's look at this again, and you can see as we scroll down along here, I've got one called zone no index. Same data, it's just I don't have an index on that field. So let's run this, and what I'm going to do is turn off the computer for a moment. Once we get it started, at least. So let's run this. So I'm going to get the count. So again, that was 87 milliseconds, and let's go zone no index. So it's just a table, but it doesn't have an index on it, just a column rather. So let's run this. So here it goes. So now it's running, and we may as well just let it keep going for a little while. So this is searching that column in a serial fashion to try and collect all the Sunnysides. Ordinarily this would go very quickly because computers are fast and we don't have as much data. We rarely work with 10 million objects, but this is becoming more and more commonplace, and that's why I have the big data analytics class. That's done, and that took 27 seconds, 802 milliseconds. So here I've got the example of milliseconds to seconds. So 87 milliseconds is really 0.087 seconds. And we can look at 27 or 23 divided by 0.087, and that's 264. So the query that we just wrote that looked for Sunnyside in this case, ran 260 times faster with an index than without an index. There are also spatial indexes as well that index geometries in a similar fashion to this. A little bit different, of course, but basically it's trying to store data and store the geometries in such a way that we can find it quickly and we don't have to evaluate it against any others. So for instance, the number 6, once I dive to the left, I'm never looking at any of the data over here any longer, so I can find 6 that much faster because I don't have to worry about any of this. Well, spatial indexes do the same thing. And if you want to learn more about the use of indexes to speed up data for big data, you can check out my big data class. But for now, this should be sufficient to show you a very important part of Postgres and SQL, and that is the effective and efficient use of indexes.